Good day, everyone. This is Group 1, and your topic for today is elasticity of matter, Hooke's law. This will be the flow of my report for today. At constant temperature, solids retain their definite shapes and sizes unless acted on by an external stress. When an external stress acts on a solid, shape, size, or orientation may change. Oftentimes, once the stress is removed, the solid will return to its original condition. When the solid returns to its original shape and size after all the stresses have been removed, then it is elastic. Before we dive into what elasticity is, what is spring? A spring is an object that can be deformed by a force and then returned to its original shape after the force is removed. Springs come in a huge variety of different forms, but the simple metal coil spring is probably the most familiar, right? Springs are an essential part of almost all moderately complex mechanical devices, from ballpoint pens to racing car engines. So, what is elasticity? Elasticity is also known as the springiness. Elasticity of a body is its ability to return to its original size and shape after being subjected to some stresses. The greatest stress for which a body can still return to its original size and shape is called the elastic limit of the body. When the stress applied to a body is greater than its elastic limit, the body acquires a permanent deformation. So here are some concepts. Stress is a measure of the forces causing deformation. Strain is a deformation caused by the stress. The greater the deforming forces, the greater the resulting deformation. This is called Hooke's law. And lastly, elastic modulus, the ratio of stress to strain, or the coefficient that relates a particular type of stress to the strain that results, is called an elastic modulus. Remember that these are properties of materials, not objects. According to Robert Hooke, for relatively small deformations of an object, the displacement or size of the deformation is directly proportional to the deforming force or load. So who is Robert Hooke anyways? Robert Hooke was an English scientist who made contributions to many different fields, including mathematics, optics, mechanics, architecture, and astronomy. And did you know he had a famous quarrel with the Sir Isaac Newton? This is the portrait of Robert Hooke. When studying springs and elasticity, the 17th century physicist Robert Hooke noticed that the stress versus strain curve for many materials has a linear region, recalling Hooke's law. This is Hooke's law of spring, a simple object that is essentially one-dimensional. Hooke's law can be generalized to stress is proportional to strain, where strain refers to a change in some spatial dimension, such as length, angle, or volume, compared to its original value. And stress refers to the cause of the change, or a force applied to a surface. From a Latin phrase, potentio sic which can be translated literally into as extension, so force, or translated formally into Extension is directly proportional to force. Most likely, we'd replace the word extension with the symbol delta x, force with the symbol F, and is directly proportional to with an equal sign and a constant of proportionality k. Then, to show that the springy thing was trying to return to its original state, we'd add a negative sign. In other words, we'd write the equation where F is the force, x is the length of extension or compression, and k is a constant of proportionality known as the spring constant, which is usually given in n over m. Now moving on to the flow of the activity, we have the objective, which is to study Hooke's law and the elastic behavior. Next, the procedure, the steps and the flow of the activity. Then, the data, calculations, and analysis, which shows the output or data of the experiment. And lastly, the conclusion, or the summary of the activity and explain the results. This will be tackled by my classmates. And that will be all. Thank you.
So for the procedure, number one procedure is open the link to the simulator and familiarize yourself with the buttons. There you can see the Hooke's law apparatus simulator on the left and the weights with an observation table on the right. Then load the mass on the weight hanger by clicking on the masses on the right. Start with 2 kilograms and record the new position or displacement of the pointer as x. Gradually increase the load by 3 kilograms until a total of 8 kilograms is loaded. Record the position of the pointer and in table 7.1 every time a new load is added. So after recording in table 7.1, the pointer position that corresponds to the 3 kilogram mass loaded on the spring, gradually reduce the load in increments of 3 kilogram duly recorded the resulting position of the pointer at each time. Take note, the mass in table 7.2 corresponds to the mass unloaded from the spring.
So for the data calculations and analysis, after filling table 7.1, we calculated the applied force on the spring, which is a weight of three objects. We used the 10 meters per second squared as a gravitational force. Afterwards, we calculated the summation of each data, which resulted to the following. The total displacement is equal to 0.12 meters, and the summation of the squared values, meters squared is equal to 0.005952, and total load is equal to 150 newtons, and the summation of the product of x and y is equal to 7.44 newton meter. So, for the table 7.2, we gradually remove 3 kilograms mass loaded from table 7.1. So, for the 0 kilogram unloaded from the spring, its displacement is 0.063 meters. For 3 kilogram, 0.04 meters, and for 6 kilograms, 0.016 meters. And lastly, for the 8 kilograms, its displacement is 0 meter. Next is the graph. For the first graph, we can see that the mass loaded on the spring increases. The displacement of the spring also increases. While for the second graph, as the mass loaded of the spring decreases, the displacement of the spring relevant to the equilibrium point is also decreasing. So in calculation, the slope of the graph during loading mass, we use a method of least squares where slope is equal to 3 times summation of x and y, the product of the summation of x and the summation of y, all over 3 times summation of x squared minus summation of x squared. So, uh, for this, we got a slope of 0.008 with a unit of in calculating the force constant, we got a value of 1,250 newtons per meter.
In conclusion, based on the graph figures 7.2, 7.3, and 7.4, we can infer that the force applied or mass under spring varies directly as the displacement of the spring. As we increase or decrease the mass or applied force on the spring, the displacement of the spring relevant to the equilibrium point does the same.